Hello, everyone. Hi, I'm Elsa Pastor. I'm an associate professor at the Technical University of Catalunya in Barcelona, and I am the coordinator of the WUIVIEW project. For those of you who might not be aware of what the WUIVIEW project is, WUIVIEW is an European action, an European project funded by the European Civil Protection Agency, the DG ECHO. And our aim is to study vulnerabilities at property scale in case of fires, and provide the community with standard methods and tools for the evaluation of those vulnerabilities. And as I mentioned last Wednesday, we've been performing simulations and fire tests for about a couple of years, and it's now time to disseminate our results and to share our findings with the community. And this is what this webinar series is about. We would like to share our findings, our methods to the whole entire community, which might be interested in fires. And today we have our last webinar programmed with our colleague Pascal Vacca from UPC. Pascal is an environmental engineer with an international master on fire safety engineering, and she's running PhD studies on CFD analysis of fire impact in properties. And she's the one in charge of developing the performance-based design methodology applied to properties within the WUIVIEW project. So today she will give us a bit of an overview of her activity within the project, and particularly focusing on how we are studying vulnerabilities of properties, how we are identifying the weak points, and how we are studying the fire impact when there is a fire incident. So thanks, Pascal, for being here today. And Pascal will give us a talk making use of a PowerPoint representation. So you will be able to see that PowerPoint through our YouTube channel. And for those of you who are following the webinar, please feel free to write comments, to write questions in the chat, and I'll make sure to include those comments and those questions in the Q&A session after Pascal's presentation. So Pascal, welcome to the session, and the floor is yours.
Thank you. Thank you, Elsa. I'm going to try to share my screen now with the presentation. So I hope you're seeing
go ahead, Pascal.
Screen. All right, perfect. So as Elsa said, today I'm going to talk a little bit about our work in the WUIVIEW project, and especially about the fire behavior and protection strategies of structures in the property, so at the property level. So when we talk about the property level, we refer to it as the microscale, so the wildland-urban interface microscale. In Europe, even though we have buildings that are made out of materials which are not combustible, we are still seeing that structures are igniting and burning and are actually being destroyed by fires, as we can see in the pictures here of the Mati fire in Greece. So what we want to do is to perform a property risk assessment to actually evaluate the hazards created by a fire approaching the microscale. So what we know from research is that the exposure conditions of a structure to a wildfire happen in three different ways. The first way is through radiation coming from a wildfire front, which can be located at a certain distance from a house, or so it can be, the distance is quite variable. The second way is through direct flame contact. This can be from the wildland fuels which are located too close to a structure, or it can be by other fuels which have subsequently ignited, which are located close to the house. And then the final way of the exposure condition is actually given by firebrands, which can enter a structure through gaps that are within it. So we can see here a few pictures also not only from Greece, but also Spain and Portugal. So we can see that this is a problem pretty common throughout the south of Europe, but also in the north of Europe when houses are made out of combustible materials. So then what we need to do is actually look at the vulnerable structural elements of a house, of a building, and to identify how the fire can enter in the house. So as we can see from the pictures, the roof and actually also the gutters, which are the parts of the house that are most exposed to an incoming flame front, and also to firebrands, which can actually accumulate onto the roof and in the gutters. Glazing systems are also very vulnerable, especially when flames are located, when there's like items burning really close to the window. As we can see in the picture here, where there's a tree that had burned and broke all the windows of the building. And then we also have vents, for example, that can, if they are not protected correctly, they are a way for firebrands to enter a house. Another thing that we need to look at is not only the vulnerable elements, but also the fuels that are located close to them. We can have two different types of fuels on a property. They can be natural, so for example, ornamental vegetation or trees that are located pretty close, but also non-natural, so artificial fuels that we have in our garden. It can be garden furniture, stored materials that we have close to the structure. For example, here in the picture, we can see there was some kind of a overhang and then some artificial fuels stored underneath. So as I said before, the roof is one of the most vulnerable elements for wildland-urban interface fires. It can have direct flame contact, when there are items, for example, trees that are burning close to the roof, or it is very vulnerable also to the accumulation of firebrands, which can actually drive a fire underneath the roofing materials, especially when there's like broken tiles or tiles have been displaced. So this opens up gaps and weakens the roof structure, as we see in the picture. As we see, this is what happened in Greece, and so this can also lead to the collapse of the roof structure. When it comes to the natural fuels, if the roofs and gutters are located under overhanging trees, then overhanging tree branches, then you will actually have an accumulation of debris, of fine fuels, such as pine needles. And if firebrands should ignite these fine fuels, then again, you'll have a fire that's actually burning onto the roof structure, on the roof structure. Vents are, as I said before, are another issue. The most common are located on roofs, but you also have them on the side of the house. And they are used mostly for air circulation. And if they are not protected correctly, then they are the way through which firebrands or a fire in any case can enter a house. Another issue that we've seen from investigating actually past fires is the issue of the accumulation of fuels in semi-confined spaces. Usually we see residential fuels, so artificial fuels, just stored underneath, whatever semi-confined space you might have, but also in many regions you can have a wood pile stacked out of the rain so that the wood doesn't get wet. So the issue in these semi-confined spaces is that when you have the items igniting in this space, maybe through firebrands arriving or the fire propagating through through the property and flames reaching these fuels. So if they ignite, then they can create a very large heat accumulation because the heat cannot escape the space. And so we see that this can actually create structural damage even to concrete structures. So for glazing systems, these are also very vulnerable to fire, to the exposure of wildfire. And they are basically places that if the glass should break, the fire then can enter the structure very easily. So, entailing the combustion then and the eventual destruction of the house. We can see the glazing system, they're made out of different components. So we have the glass, of course, but also what's important is the frame. Frames are usually in the south of Europe are made out of aluminum or PVC and wood, even less often. And older houses have single pane windows, so with very thin glass, while now the newer houses do have double pane and a bit of a thicker glass. Cracking of the window panes is frequently observed in forest fires, particularly because of flame impingement, as we can see here, the tree igniting very close to the windows. But also what makes the windows cracks as well is the temperature difference between the hidden part of the glass and the part that's exposed to the source, to the fire source. Should the frame fail, then we also create a displacement of the whole glass system. So we also need to consider a failure of the frame because this can also create an opening through which the fire can enter. Shutters are also, fairly used, and they are actually very good at protecting the glazing system, so the window. However, we have seen also again from past fires that PVC actually melts. So PVC shutters are not a great option because then with the melting of the material, then you are exposing the glass to the heat source. So wood and aluminum have been shown to perform better at protecting the window. And then another thing we need to consider is the vegetation management around the property. This can minimize the impact of the fire to a building. There are recommendations that established a 50-meter radius in which the fuel management is prescribed. You can see the first two pictures. This is not done. You have, the wildland fuels very, very close to the house. You have here trees with branches that are hanging over the roof, and then grass, going basically until the walls of the house. But then we also need to consider the ornamental vegetation that we place in our gardens. So if our garden is clean if the property is clean from wild fuels, but we have, for example, hedgerows, these are also a big hazard because if they ignite, they can pose not only a threat to the structure if they are located close to it, but they also allow for fire spread through the property. And actually, if there's a continuous hedgerow going through different properties, then it will also aid the fire spread through the settlement, so not only through one person's property. So we can see here, for example, in the third picture, where the hedgerow had ignited and actually created damage to the windows of the house. So how do we analyze these risks and the structural vulnerability in a quantitative way? So we do this by using the performance-based design approach. This is used also for fires that happen inside a building. So we're basically taking the same approach, but changing the fire scenarios and the objectives to apply to situations where the fire is attacking a building or a property from the outside. So this is an approach based on fire safety goals and objectives, the analysis of different fire scenarios, and then finally the quantitative assessment of the design. Here is a little bit like how it works. It's a little layout of the steps of the performance-based design approach. So first of all, we need to define the scope of the project. For us, in this case, the scope is the property. One property at the wild and urban interface, can be more than one. Then we go to the identification of the goals of the project. In our case, mainly we talk about life safety and then property protection. Life safety, for example, if people want to shelter in place, and property protection, of course, we don't want to lose the structures. We want our structures to not burn down. And then we define the objectives of our project. And so for us, mainly we look at occupant protection and then structural integrity. The next step of a performance-based design is to define performance criteria. So depending on what we are analyzing, we need to define the criteria. And if the criterion is met, this means, for example, that the building is safe or that the occupants are safe. And if it's not met, if we overpass this criterion, then basically there are some issues and we need to reevaluate our project. Performance criteria can be temperature thresholds, smoke concentration, radiant heat fluxes, any item, any subsystem of a structure, for example, will have its own performance criteria. Then we go look at the scenarios and the design of the building, for example. And we need to select different scenarios. There's a variety of scenarios that can be interesting to analyze. However, we cannot analyze all of them. So we need to make a selection of which scenarios can be representative. So for example, we can look at scenarios that could happen with high frequency, but that have low consequences. So let's say, for example, we have a property and we have a wildfire approaching, and then some garden furniture ignites, but the garden furniture is located far from the structure, all the windows are closed, so we are going to have probably low consequences. So we could analyze this type of scenario. Then we can look at the low frequency, high consequences scenario. For example, all the items that are located on your property are ignited at the same time. What happens then? Or you can look at special issues. I don't know, do you have like an LPG tank on your property? Do you have a porch, a semi-confined space? So yeah, these are the different options for the scenario selection. And then finally, what you need to do is to develop some trial designs that you're going to evaluate to see if your project, if your design is safe or not. So here we've developed a little fault tree to identify the scenarios that are important for us, given what we've seen, from the investigation of past fires. You can see that we have some basic events. For example, we have what happens when we have poorly designed or maintained vents, or poorly managed roofs and gutters. For example, I'm going to go over a scenario. Let's say that we have a poorly managed property, and then we have natural fuels that are close to the structure that are ignited, and also, for example, non-natural artificial fuels. So let's say our garden furniture has ignited. Then if they are located close to the structure and there's a window, then the window is exposed to a fire that's very close, and then the window will break if we have unprotected glass. And this will lead to the fire entrance inside the structure. So yeah, a fault tree is a good way to identify the possible scenarios and see also which ones are, the most, let's say, the worst case scenarios. So how do we evaluate then our design? We do this through fire models. We use CFD tools, for example, FDS, the Fire Dynamic Simulator, which is a model of fire-driven fluid flow, and it puts emphasis on smoke and heat transport. So it's been validated. This FDS has been validated, and it has shown to give good results when it comes to simulations where there's a fire involved. You can analyze your design at different levels. You can do a subsystem evaluation, so where you, for example, look only at the glazing systems or only at the semi-confined space, or you can look at the system, which involves more than one component or one protection system. And then you can also look at the whole building or the whole property. So this allows for different levels of evaluation. And here you can see some pictures, some examples of what a simulation looks like in FDS. So here we have a house exposed to a fire. This is actually the simulation of a hedgerow burning. And then we can see the incident heat flux onto the different surfaces caused by this fire. So first of all, we analyzed some subsystems, and we looked at one of the most vulnerable parts of a house, which is a glazing system. So again, we looked at the steps of the performance-based design, and we set the performance criteria for a glazing system. So this is in the research, in the literature, you can find information on this, but basically we have a temperature threshold after which the glass will break or start cracking, and then also a received heat dose. Then we look at the window design. How our windows? So do we have a single pane? Do we have double pane? What's the thickness? Can be 3 millimeter, 4, 6 millimeter. And then we look also at the frame. What material is our frame made out of? Or we could also include some shutters. For example, we can include, let's say, PVC shutters. Then we know that after a certain temperature threshold, they will start melting. So what happens to the glass located behind the shutter? And then, of course, we want to analyze the fire design. So we want to analyze the fire that's located in front of the window. We can have a natural fire source, so ornamental vegetation burning. a non-natural fire source, our garden furniture is burning. And also we should look at scenarios where we have no wind or where we have some wind, which allows for flame impingement onto the window. So the good thing of FDS is that you can run a lot of scenarios with a relative, in a relative small time. So you can, look at different distances of your item from the window, for example, to identify what's the distance at which the glass will not break. You can add the wind at different wind speeds, different wind directions. So yeah, it's a really good tool to perform, the analysis of different scenarios. Another subsystem we've been looking at is the semi-confined spaces. So basically, we place some artificial fuels that are stored, and let's say this semi-confined space is used as a storage area. And we look at the load-bearing capacity of the walls to see if this fire will will damage the structure or not. So again, we set our performance criterion. We look at the design of the semi-confined space. So what materials are my walls and ceiling made out of? What's the thickness? What's the geometry of it? And then again, we need to choose a fire scenario, a fire to place inside this semi-confined space. So here we could analyze, for example, we placed, I think it was a stack of wood pallets, stored below this space. And then we placed temperature sensors on the walls. So we could, FDS could give us the temperature through the whole thickness of the wall. And then we looked at the load-bearing capacity of the walls. And here we can see that the blue line is going below. So the capacity is going down from 100%. It's going below 80%. So for us, this is already, kind of a dangerous scenario, especially if this semi-confined space is attached to the walls of the main structure. So to the walls of your house, because this could create structural damage to your house. Then we not only looked at the structural vulnerability, but we only looked at the sheltering capacity of a house. So shouldn't there be enough time for you to evacuate? Can you safely stay in your house? Like, will you be sure that your house is not gonna start burning? So we need to look at some other things when we talk about sheltering, because now we also need to look at the smoke hazards, because you can have irritant fire products which can cause painful effects, for example, to the eyes or the respiratory tract, and then also the asphyxiant fire products which can cause incapacitation. So in this case, when we look at sheltering, our performance criteria are set for the house, for the building. So can can the building withstand the fire? But also we need to look at the tenability inside the house. So are the temperatures gonna be, low enough so that person can survive in there, or the heat, same thing with the heat flux. And then we need to look at the survivability. So in this case, we look at the fractional effective dose, which is basically the length of time that an individual can be exposed to a particular toxicant before succumbing to the effect, so before dying. So after this, after the performance criteria are set, again, we look at the building design. Can the structure survive? Are there any openings or leakages through which the smoke can enter? But also, what's the best a location in the house for you to shelter. For example, what's the place where you know that the temperatures are not going to be too high. And then again, we need to look at the fire scenario. What fire are we going to place, close to the structure? What could be the worst case, for example? So we need to look at the location of the fire, also what type of items are burning. Is it wildfire? Do we also have some toxic products coming, for example, from garden furniture that's ignited? So in this case, we also need to look carefully at the combustion products. So after analyzing all this, we came up with some recommendations for the structural elements so that a structure can survive a wildfire passing through. So we've seen that for glazing systems, smaller windows are better than the bigger ones. They resist more than bigger windows. As I said before, frame materials which have a low melting point are not good. For example, PVC is not that great. So we would prefer aluminum, for example. Then it's best to have double or multi-pane windows with a thickness that's ideally equal to or more than 6 millimeters per pane. They resist more than, for example, the single pane 3 millimeter glazed glass that is found in the old houses. And then if you have shutters, that's great to protect your window. However, it's best to again use materials such as aluminum or wood. For semi-confined spaces, we have seen that if you use them as storage, so if you actually have there's a big fire load that's placed in these spaces, it's best to have them independent from the frame of the main structure, so that if damage happens, then you're not damaging your house. And then for roofs and gutters, it's best to to have some tiles made out of clay, so to use fire-resistant materials. However, for the gutters, aluminum gutters might stay in place. So if there's some debris, some fine fuels in there which get ignited, then the fire that's going on inside the gutter can actually be more damaging to the roof. So PVC, we've seen that like PVC gutters, they melt and they basically drop the fire source to the ground. So this can also be better way of protecting your roof. And then it's best to avoid shapes that can create an accumulation of debris and firebrands. And of course, periodic maintenance and cleaning from the debris is the best. And also, keep away the trees from the roof. And then for vents, we've seen that, if they are covered with adequate meshes, then you have a solid protection system. And then again, when it comes to vegetation, when it comes to the ornamental vegetation, it's best to use fire-resistant species in your garden, especially when these are located close to the structure, to the house. Avoid some fuel continuity on your property. So I said there's like a 50-meter radius at which you should have a lower fuel load, and also you want to avoid creating this discontinuity. So in order to avoid the fire spreading through the vegetation. As I said before, no vegetation over the roof, and place ornamental vegetation at least 4 meters from the windows. This we've seen by simulating, different fire sources located close to glazing systems. And then also very important, the periodic cleaning of the ground fuels, especially by close to the hedgerows. When it comes to the artificial fuels that you might have on your property, these fuels actually usually burn for a longer period of time compared to the vegetation. So they might give a lower heat lower heat fluxes onto the structure, but then if they are burning for a long period of time, then your structure is exposed for, I don't know, 30 minutes to a fire, and this might create some damage. And again, no storage in semi-confined spaces if they are located close to your house. So with these recommendations, we've actually created checklists, which are a self-assessment tool for the owner to go. So the owner goes through the checklist and he will get an idea of how safe his house is in case of a wildfire. So it is a vulnerability assessment tool, which gives, as a result, a fire vulnerability index, which is a value between 0 and 100, where 100 is the worst case you can have. And if you have an FBI lower than 20, then you can assume that your house will be safe in case of a wildfire. Another checklist, another tool that we created is the sheltering assessment tool. This is if people wish to shelter in place, and it is mandatory for the owners to first see if there are any vulnerabilities when it comes to the structure. So the FBI should be lower than 20. If it is not, then shelter in place is not an option. Then you should evacuate before the fire reaches your property. And also you must be in a fit physical and mental state, and you must be prepared to respond in case there's fire brands igniting some fuels on your property. Then you must be able to respond to that. So after all this, we decided to look at a real case study. So go to a real wildland urban interface property and apply the performance-based design that I've mentioned before. So here we analyze the property here in Spain. You can see the property is located at the border of between the settlement and the wildland. And I went through the checklist and we saw that we have a FBI, a fire vulnerability index that's equal to 61. So we are well above 20, which is our, ideal value. So then we decided to analyze the risks and the vulnerability of this property in a quantitative way. So the goal, again, is property protection. We are assuming that the owner will not shelter in place because his FBI is higher than 20. And the objective is to maintain structural integrity so that there will be no ignition of items inside the house. So no burning inside the house. We can see here there's a hedgerow surrounding the whole property, which is actually linked to linking the analyzed property also with the neighboring ones. And we can see from the picture A that we have a nice porch with a very big window. So lots of windows on all sides, on all facades of the house. So in order to meet our goals and objectives, we need to set performance criteria. For the glazing systems, again, this is the temperatures they are exposed to and the heat dose they are exposed to. While for the porch, for example, or well, if we have something burning on the porch, then we want to look at structural integrity. So look at the load-bearing capacity of the walls. And then here, if we want to, for sheltering temperatures, heat flux, and FED. However, as we said before, nobody will be sheltering in the house, so we can take out that part. So for the fire scenarios, we can look at a high frequency, low consequence scenario. For example, we have a fire spreading through the hedgerow where there's only one ignition point, and the fire spreading only through the hedgerow. We have, let's say, average seasonal temperatures, humidity values, and wind. We don't have any extreme environmental condition. Second type of scenario we could analyze is a low frequency but high consequence scenario. So let's say that fire brands ignite simultaneously all the vegetation located around the house. So the trees and the hedge are igniting all at the same time. And we have peak seasonal temperatures and the lowest seasonal humidity. So basically our vegetation is dry. And then worst case wind direction and wind speed. And then a special issue that we have in this case, as I said before, is we have a porch where we can have garden furniture, and there's a very big window located on the porch. So the trial design, in this case, we decided, okay, let's analyze the house, the building as it is now, to see if it's safe or not in case of, a special issue scenario where we put a garden furniture burning on the porch, as you can see here in the picture. So we ran the simulation and evaluated the scenario, and we can see that the porch window would actually break after 2.6 minutes from the start of the fire. But from the graph of the load-bearing capacity, we can see that fire is not big enough to create structural damage to the walls, or because you can see we are going well above the 80% capacity. You can see that from the blue line in the graph. So basically, we have met the performance criterion for our walls, but not for the windows. So the window will crack, will break, and the fire will be able to enter inside the house. So in this case, in this scenario, the design, the house as is, does not meet the performance criterion set for the windows. And so we need to modify the design. And thank you very much. I'm at the end of the presentation. I don't know if there are any questions or...
Sure, Pascal. Thank you very much for your presentation. You can stop now sharing your screen. There are many comments in the chat related to many different topics that you have talked about. For instance, we have comments on residential fuel hazards, either natural or non-natural. We have also questions about the PVD methodology itself, how we managed to get all the information ready to go, and also about particular systems under analysis like glazing systems, etc. So I'll start taking those questions for you, Pascal, now, and I'll start with the residential fuel hazards. The first question is about hedgerows. We were discussing hedgerows last week with David Caballero as well. We discussed about hedgerows with our firefighters, Edgar Nabot from the Generalitat de Catalunya, and now we have had the opportunity to to discuss. We have the opportunity to discuss with Pascal, the one who has been doing all the simulations about hedgerows. And the question is as follows. At which distance a hedgerow can be placed to consider it safe for the structure in case it burns? You have just mentioned that in your study, you've come up with a distance of 4 meters of overall ornamental vegetation. So that distance, would that apply to hedgerows? Could you provide us with a little bit more of information about hedgerows?
Well, it depends. It depends on, on the type of hedgerow, on the moisture content. Is it, for example, very dry or not? From what we have analyzed, 4 meters is an okay distance, also for when you involve the wind. However, we have analyzed at the moment only dead or very, very dry vegetation. This is a bit of a limitation of the software that we are using at the moment. So yeah, for sure we need to look at it some more, but for now the results with dead trees, with dead vegetation, which should be, ideally a worst case, are showing that 4 meters are okay. But, again, with the window size that we are analyzing, with the type of frame that we are analyzing, so it's very variable depending on, also on the construction of the glazing system.
Right, of course, but at least we could conclude that we have at least put out the method to analyze all those different conditions.
This is shown, and 4 meters. This is with wind as well. So we have, the wind blowing the flames towards the window. Mm-hmm. So
right. Let's move on now to non-natural fuels, because we have also here a question regarding LPG tanks. The question is whether we have studied LPG tanks and if they seem to be safe in a WUIVIEW scenario. Could you talk about that as well?
Yeah. So we've been analyzing LPG tanks as well. We have seen also from past fires that there is an issue with this type of artificial fuel because it's something that's not very pretty. So you want to hide it when it's on your property. So what you do is you place, a hedgerow around it. And then if this hedgerow ignites, then you have, very big heat load onto the tank. So yeah, we are looking at this tanks close to residential fuel, so both natural and non-natural, and we see that the danger is that if the liquid is heated too much, then the pressure release valve will open, and basically what you do is you create a jet fire, which then can compromise other elements on your property. So yeah, we will have actually a video coming up just about the analysis of LPG tanks.
All right. Yeah, sure. We will also update you with more activities, with more dissemination activities that we will be exploring in the next weeks in the WUIVIEW project. Now let's move on to the PBD method, particularly highlighting questions about performance criteria and about FAR inputs, right? The first question is about performance criteria. Is it easy to define the performance criteria for the WUI? And are the values used in compartment fires somehow applicable?
It depends. It depends on what the subsystem that you are analyzing. For example, for glazing systems, we have seen that, so there's a lot of information in the literature about, at what temperature will make the glass crack. However, most of the tests, the experimental tests, are done in scenarios where you are kind of looking at compartment fire. So basically you will have, much higher temperatures. You will have a smoke layer coming down. So it's a little bit different compared to the scenarios that you will have with a fire at the outside. So yeah, for sure there's a lack of information on some subsystems to see, what's the best criterion to use. So yeah, we need some more research about this.
Right. And the second issue about the methodology is about the fire inputs. Because as some of you may know, we have to prescribe fire curves, heat release rate curves of elements burning, so that to prescribe actually the fire. So is it easy to find those fire inputs, or are there any options to get not prescribed fire, but actually a fire being simulated with FDS? Could you provide us with more information on that?
Yeah, so when you look at the performance-based design approach for a fire inside the building, many guidelines will actually give you a fire curve, or like a peak heat release rate, or a heat release rate per unit area, because a lot of research has been performed on what type of fire, what type of heat release rate would you have, for example, in an office space compared to a hotel, compared to an apartment. This information lacks for when it comes for the wildland urban interface, so fires that are coming from the outside. There's not a standard value that you can use. It really depends on what you actually have there on the property. What type of non-natural fuels do you have? What type of natural fuels do you have? Vegetation varies a lot. And also there's if you wanted to actually prescribe something, so you are saying like, okay, I have this type of item on my property, can I find information on how this item burns? This is also a bit tricky, because many tests have been performed on items that are commonly you can commonly find in an office space or a home. There's a lot of information on how a couch burns, for example, but we don't have a couch outside usually. So we are lacking information on artificial fuels, like how artificial fuels located in our properties are burning, but also on how our vegetation is burning, what type of curves we are getting from the ornamental vegetation, for example. Yeah.
Yeah, so I might link this answer with the very last question that I've read in here, which is, are you using the fire inputs from fire tests for the real case studies?
Yeah. Yes, we are for the artificial fuels. When we are simulating those, for example, and I showed you the garden furniture. Yes, you can find some information in the literature, as I said before, but also we have performed tests on artificial fuel packs. So we place different types of fuels together, and we have ignited them. So we have actually analyzed the burning behavior of these fuels, and then we are able to place those in our simulations.
Okay, so and now let me just take another general question about the PBD method, which is about the computational cost. There is a question in here, which is, what is the computational cost of PBD simulations? Could you provide our audience with a little bit of information on that?
Yeah, it's very variable. It really depends on what type of fire simulation you are performing. So in FDS we have two options basically. One option is to use particles, and this is very it takes a long time to run a simulation if you are igniting particles. So if you are simulating vegetation as particles, so can be like a 1 month simulation, while if you are burning, let's say, the garden furniture, simulations that I showed you in the presentation, that's about a 4-day simulation using 44 cores, so a decent size computer. So yeah, it's very variable depending on the type of fire that you want to simulate.
Right. So the next block of questions, Pascal, they deal with very specific details of the simulations that we've been performing in the WUIVIEW project. Hopefully we're going to get time to go through all of them. The first question is about the glazing systems, the simulations on glazing systems. And the question is as follows. What is the effect of the wind on the time it takes for the glass to reach threshold temperatures for the glazing?
Yeah, well, of course, it's gonna speed up the process. So especially if you have flame impingement, then your window will crack sooner. However, we have seen if you place the item far enough, the wind is actually acting a little bit, having a little bit of a cooling effect on the window. So yeah, if it's close, then and you have flame impingement or very close, flames very close, then it will speed up the process for sure.
Mm-hmm. Another very specific question. It's about heat fluxes, okay? And it is as follows. What are the differences of the incident heat flux with different vegetation settings? For example, high vegetation height or moisture level or bull density or vegetation structures. So are you picking those differences in incident heat flux according to different characteristics of the vegetation?
Well, at the moment, because of the the limitations with the software, we have only analyzed kind of one type of vegetation. So yeah, basically we're looking at a very low moisture content. So we haven't. It's work in progress. We are still looking at this, but yeah, there are some limitations.
Right. Again, another specific question now related to the capabilities of FDS, which is the tool that we are using for PVD simulations. And it is, I've lost it. I have lost it. It was about fire protections. Oh, yeah, here it goes. Did your software be able to add the effects of active fire suppression systems?
We have not analyzed those. The software can, for example, simulate sprinklers. This is just an example. However, it's very it's at a very high computational cost. So this is why you make assumptions actually more than simulating the the actual water on fire. So you make assumptions and you say, okay, by this time I'm gonna have some suppression going on, so I will cut my heat release rate curve, for example. Yeah.
Right. There are also some discussions about the standards and the codes regarding fire-resistant species. We have talked about the role of ornamental vegetation. So there's a question whether we are aware of standards or codes in the literature for fire-resistant species and what are the characteristics that make those species fire-resistant. And then there is actually an answer coming from the audience as well, that there are several publications of rankings of species. That is true. There are some works done here in Spain, so we would be happy to share those references with the audience as well. I guess that maybe the link of those guidelines can be easily shared through that chat window. And so I guess that we still, it's 5 o'clock now, but I guess that we still can take the very last question of our webinar, and this is regarding the checklist that you have just shown, summarizing, let's say, the findings that we've been summarizing with the FDS simulations. And it is the question is as follows: have you checked the situation of weak communities with the SAT, with the Sheltering Assessment Tool questionnaire anywhere? Have you done tests with that?
At the moment, I think that when we went to look at the buildings, most of them, if not all, reached a FBI value higher than 20. So that I know of, like, this is already one of the criterion to exclude the shelter in place thing. But yeah, basically, I don't know, Elsa, if you have some more input.
No, the thing is that indeed we have been testing the questionnaires in its very let's say alpha version, and we went last summer to test several communities, particularly in Portugal, and as you have just mentioned, the criteria to set whether that structure would be a good place for sheltering or not was basically based on whether that structure would have structural integrity or not. So meaning that if you have structural integrity, then it could be safe for you to remain in place. But as you have just mentioned, there are many other issues that have to be completed within that questionnaire, which actually relates with the physical and the mental state of people which are around, that if they can make, let's say, an active role during the fire. So we haven't done that, but hopefully we're going to have other opportunities in other European projects to scale up those tools and to make those available for the entire community. Let me take one last question, Pascal. It is 2 minutes after 5, but there is just one little question that I would like to take, and then we can finish. And it's about scales. We have been talking about the micro scale, that is the property scale, the homeowner scale. And the question is about coupling scales. And it is, how do you couple finer analysis scales and grid resolution of CFD simulations? If we want to move from one scale to another, would that be feasible or easier with CFD tools?
I think it's feasible up to a certain distance from the house. The good thing with FDS is that you can increase the mesh size. So we have seen, actually, there are examples where mesh sizes have been used, to simulate wildfire. I think it was 5 meters by 5 meters, so it's very large. So then you can cover a very large scale, and then you can go finer and finer once you reach the property. So what you want to, what you are looking at. So I think it also really depends on your computational resources as well.
Mm-hmm. Yeah. All right, so we don't have time for any other questions, but indeed, I guess that we have answered them all. Thank you all for being here. It's now time to close the session. Just let me remind you that please stay tuned, because we're going to make some interesting announcements soon next week. We are about to program our final workshop. It's going to be held virtual. Unfortunately, we cannot have live sessions being all together in the same room, but we will be very happy to share with more details and devoting more time to that, our results and our methods in the final workshop that's going to take place around mid-January, let's say. And in order to get you ready for that final event, as Pascal has just mentioned, we will be uploading some videos of the main activities just for you to get a refresh of what we've been doing during the first half of the project. So I hope to reach you all by then, for our final workshop. And that's all from our side. Thanks for being here during this webinar series. Thanks, Pascal, for your time today. And you all take care and stay safe. Bye-bye.